In this video, we're going to take a look at an example of a system of autonomous differential equations. And so what we mean by autonomous is that this differential equation doesn't depend on time directly, and this doesn't depend on time directly, but indirectly they do. So if time changes, then x changes, and that in effect is going to have a change on y. So first we want to write out the phase plane equation, then we're going to solve that resulting differential equation, and then we can show what the results, what the solutions are going to look like in the xy phase plane. So to set up the phase plane equation, we're going to find the formula for dy dx. And so recall to find that formula for dy dx, by applying the chain rule, we would take dy dt and divide by the differential equation for dx dt. So put the y on top, the x on the bottom. So on top, we have the equation for dy dt minus 2x, and on the bottom, we have the equation for dx dt, which is 7y. And notice this is a separable differential equation, so we can separate and bring the 7y to the other side. So we have 7y dy on one side. We bring the dx to the other side, and that gives us minus 2x dx. Integrating both of these sides, on the left side we would have 7/2 y squared, and on the right side we would have minus x squared, and then we have an arbitrary constant that I'll put plus c. And so if I bring the x squared to the other side, that gives me x squared plus 7/2 y squared is equal to c. So that would be our phase plane solution. And if we want to graph this, which is the next part, then this almost looks like a circle, except we have that 7/2 in front of the y squared, and that's going to make this an ellipse. So each of these graphs in the phase plane should be an ellipse. And for each value of c, we're going to get a different ellipse. And so one thing that we should note here is that at minimum, c can be 0. And so if c were a negative number, there's no way that we could take x squared, which is going to be at least greater than or equal to 0, and add it to another term which is greater than or equal to 0, and wind up getting something negative. So the smallest value for c that we could pick would be c equals 0. And so when c is equal to 0, the only points that are going to satisfy that equation would be those single point 0, 0. So that's kind of a singularity there. If we think about c being equal to 1, then we've got the equation x squared plus 7/2 y squared is equal to 1. We have an ellipse, so if we set y equal to 0, we would get the x-intercepts at minus 1 and positive 1. And if we set x equal to 0, then we can find the x-intercepts, the y-intercepts at 0 minus the square root of 2/7 and 0 plus the square root of 2/7. So given the x and the y intercepts, we could plot over here just a very informal graph of this. So the major axis goes along the x-axis, and the smaller radius would be along the y-axis. And we can spread this out and look at solutions for different values of c, and that gives us this kind of bullseye of ellipses. So in blue, I have the curve that I sketched very roughly down here. And as we increase the value of c, these ellipses are getting wider and wider, minor and major axes. And somewhere in the middle here, or exactly in the middle here, we kind of had this degenerate case when c was equal to 0. We just had the origin. And so again, one thing that you want to be careful about is we found a solution in the phase plane, but we actually don't know how x depends on time and how y depends on time. So we haven't solved for x and y, and there is a time component in this system that we miss if we just look at the phase plane diagram. So for example, I don't know which way we're rotating around this. Am I moving clockwise or counterclockwise around these curves over here? But we can figure that out by thinking about the signs of dx dt and dy dt. So for example, if I were right up here at this point on the curve for c is equal to 3, for this point, what we know is that x is 0, y is not 0. In fact, y is a positive number up here. And so if I were to plug in 0 for x and a positive number for y, then that value would be positive. So that means dx dt being positive means we would move in the positive x direction to the right. So if we're moving to the right over here, that means on this curve we must be moving in this clockwise direction, and the same would go for the other one. So over here we have all of our trajectories are moving in the same direction. So we would call these graphs in the phase plane trajectory, and we've got all of these things rotating in the clockwise direction. So even without finding solutions independently for x and y, the phase plane is going to tell us exactly how the values x and y are related to each other. And if we indicate some direction of the flows along these trajectories, then we can see how time is playing a role in this picture.